Alright, this is a example of using bearings and law of sines, law of cosines, depending on how the information falls. So here I just made up a little story. First officer of a carrier set off at a bearing north 22 degrees east and traveled for 120 miles from the port. Then he ordered a new bearing of south 78 degrees east for another 80 miles, and then came to a stop, something that a carrier would never do. But we needed to be still for this problem. The captain set out for the carrier at this position in a jet from the port. So what we want to know is what will be the captain's bearing and how far will she have to fly. All right, so let's put in the information into the picture. Here we have this north 22 degrees east, and I have the vector of the boat going in that direction. So this angle here has to be 22 degrees. Then the other one, after he changes his course, he's going to go south 78 east. Now to get the bearing straight, you need another north, south, east, west coordinate system. And since he's going south and then east, this other angle here is going to be 78 degrees. Now the problem with this is a lot of the angles aren't known, but some of the sides are. Like this side here is 120 miles. And this side over here is 80 miles. So what we really need is this angle over here. We'll call it theta of this triangle. Now, we could find theta. We have the opposite side, but we don't have this angle over here to find this opposite side. So we could use law of sines if we knew this angle. But this one's going to be actually a side angle side setup, so that's going to be law of cosines. So the important one is the measure of that angle right there. To figure that one out, we just have to realize that this line and this line are parallel, and this vector that's cutting through them is called a transversal, and this angle are what is known as alternate interior angles. Therefore, they're exactly equal. So that angle there is also going to be 22 degrees. This angle and this angle are congruent. All right, so we know this main angle up here is going to be 100 degrees after we add them together. So we got a 100-degree angle in this corner of the triangle, and we have the two adjacent sides. So we can set this up as law of cosines. So let's see here. So we have 100 degrees in here, oops, for this whole angle. We have 120 on this side, we have 80 on this side, and what we're interested in is two things. We're interested in the distance that the captain has to travel, and we're interested in this angle theta down here. Now, law of cosines can come up with the x rather quickly. So let's set it up as c squared equals a squared plus b squared minus 2ab cosine of big C, where big C is going to be this angle here. Now, it really doesn't matter which ones you call a or b, so I'll just kind of put them in there. Therefore, this is little a, this side is little b, and this side is little c. All right, so we're looking for, let me back up. I'll put the proper letter in there. We're looking for x, so we're going to substitute it in, x squared. A is 80, so 80 squared. B is 120, and then just kind of 2 times 80 times 120, and then cosine of 100 degrees. Now, when you type all this mess into a calculator, take its square root, you get x is approximately, not exactly, but approximately 150 miles, if I round to the nearest mile. So that tells us how far the captain has to fly in that direction. So let's make this 150 miles. All right, so now I want to find theta. Well, theta is related to A, and we know side A. Now I have side C, and I know angle C, so we can set this up as law of sines. All right, so we get, we're looking for an angle, so let's put the sines up top. Sine of A over little a, which is 80, is equal to sine of 100 degrees over C, which we found to be around 150. Now, I don't usually like using rounded numbers in a further calculation, but we have no choice here. All right, so we're trying to solve for A, and therefore we should just multiply the 80 up. So we're going to get sine of A is equal to 80 sine of 100 divided by 150. And when we do sine inverse to get rid of the sine, and we have to be careful with the sine inverse because it could be an obtuse angle, but I know for sure that angle A is not going to be obtuse because this angle up here is 100 degrees. That only leaves 80 degrees between these two. So we're guaranteed sine inverse is going to give us the right answer, that it will be a first quadrant angle. Okay, so what we find here is the measure of angle A is going to equal, well, it's going to be approximately 31.7 degrees. So this angle here is 31.7 degrees. And this angle here is 22 degrees. So the new bearing is going to be the sum of those, which is 53.7 degrees. And we're heading north, east. So here's our bearing. The captain would have to have this bearing and travel for 150 miles to land on the carrier.